Hi students, I am Dr. Badrinath, and in this video we will see the size reduction theories. Size reduction theories is different from principles. Principles I have already completed one video on that. In this video we will see only the theories. That's it. The center part of this theory or this video concept is breakup. Breakup. Breakup means, first of all, initially we thought it is a love breakup. Before love breakup, first we will see how the particles will be break up. Then only the size reduction will happen, right? And who are all the scientists who developed various theories how the particle is break up and all that we will see in this video, right? And main first thing, breakup is the center point of this video. And why this breakup or particle breakup or love breakup, why this happens means mainly due to the stress and strain. Stress causes the strain, keep in your mind. Stress causes the strain. Due to the strain only, the particles will be break up. That keep in your mind. Strain, how the strain come from the stress. See how in the office she is working. Number of persons they came and giving the work. So she's feeling very hectic stress. All this stress means some people they can handle the stress very easily, but generally it is not possible for a human being. So they will get a full strain and all. That strain leads to crack. Crack leads to break. That is a simple concept. Stress leads to strain. Strain leads to crack. Crack leads to break. Okay, crack is different. Break is different. That we will see what is the difference and what is this stress strain diagram. That and all we will see in this video. Very important concept in all theory examinations and all whatever you can say, the competitive examination, regular examination, this concept is very important and very simple also. Stress strain diagram. Stress strain, the two things. Stress means y-axis, strain means x-axis. If you are increasing the stress, strain is increased. See here, directly proportional. Directly proportional. See here, stress and strain, and see the curve, linear, very linear. It is go on increasing. Strain, as you are increasing the stress, strain also increasing. Here you take the example of rubber ball. Here I took a rubber ball. Instead of rubber ball, you can take a rice grain or paracetamol particle or ibuprofen particle, any antibiotic particle on which we are going to be put a stress. That particle you can imagine here. Now we will take a particle. Suppose say here I took a rubber ball. I put a stress on this. So when I put the stress on this, keep on putting stress on the rubber ball, it becomes a oval shape. See here, oval shape. Round ball become oval shape. In the same fashion, any particle also, up to certain extent, if you are giving a stress and all, it will be shape out. It will be shape out. And keep in your mind, here see, oval shape is there. When you release the stress, again it comes back. Again it comes to the round shape. So, rubber ball is able to tolerate the stress up to certain extent. See here, up to this extent. This point is very important point called as a yield point. Yield point. Keep in your mind, very key yield point. If you keep on increasing the stress on the rubber ball, up to this it can tolerate. And later what happened? No, it develops a crack here. See here, I have shown with a black mark. Small crack will be there. This crack is again, if you are keeping a further stress, it is breakdown. See here, this is a breakdown. Here there is a crack. Here it is a break. Crack is different. Break is different. Break means complete separation. Crack means just having some crack. Okay. And keep in your mind, yield point is very important. Up to the yield point, if you remove the stress, again particle will become a original shape. That is called, that's why it is called a elastic, just like a rubber, elastic rubber. Keep on putting a stress, stretch it, stretch it, stretch it, so it feels a strain, and you release it, again it comes a original shape. But if you are pulling with much stress, there is a crack and there is a break. The things will happen. That's the way how the love breakup. Here I shown with the love breakup. How, see, why means always putting a stress, 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 stress. Okay, so one time, no, they can tolerate, they will tell a breakup. So yield point, see here, where the crack will develop and it leads to a break. So yield point is the key point here. Up to the yield point, you can say it is a elastic deformation. After the yield point, plastic. See, it is a elastic because reversible. Reversible is possible. Here, once crack is developed, even though you are removing the stress, no chance at all. It compulsory, it has to break down. This is called a plastic deformation, opposite to that of the elastic. Elastic is different, plastic is different. Keep in your mind. And here, up to the yield point, there is a Hooke's law. Hooke's law, just like a small hook. Hooke's law. Keep in your mind, Hooke is a scientist. He only developed this one, and curve is also linear. Here, Young's module, it is a non-linear. Here, see how the curve is. It is a not linear. Here, it is a see. It is a linear. That's why this stress strain diagram is very, very important and very easy also. Yield point is the center point. Young's module is there, and Hooke's law is there. Very simple. Okay. So all the particles, whatever you are keeping in the hammer mill, cutter mill, we are gone increasing the stress on all the particles. So hammers will increase, cutter will increase, blades will increase, scissors will increase the stress. Finally, at one fine point, it shows a breakup. Particles, cracks, breaks will be developed. Keep in your mind. Stress is directly proportional to the strain. If stress increases, strain also increases. If stress decreases, strain also decreases. Okay. Important features of the Hooke's law. First half of the curve up to the yield point. Up to the yield point, Hooke's law. After the yield point, Young's module. Keep in your mind. Here it is a elastic deformation. Here plastic deformation. Reversible is possible. It is a irreversible. It is a linear curve. It is a non-linear curve. Hooke's law to remember. Here I have shown a hook. Here I have shown a symbol of Young's module. Very important, this one. No yield point for a stress ball. How much you stressed ball. That's why it is called a stress ball. Name itself indicates. Even though you are stretching, it catches entire your BP, your pressure, it tolerates. The material is like that. The material is like that. So be happy, no BP. Go on pressing the ball. That's it. So very important. I told now breakup is the center point of this video. Breakup. Break comes from the crack. Crack comes from the flaw. Flaw. F-L-A-W. Keep in your mind. See, here I will show you the particle. The complete separation is there. This is called a breakup. Breakup. This breakup, before that, crack. See how this you can find these lines. This is called as a crack. Crack we can see with our eye. Some of the cracks we can see. And cracks, how the crack will develop? Crack will develop from the flaws. These flaws we cannot see directly. Any solid particle, it consists of a flaws initially that we cannot see. Under the microscope, we can able to see up to certain extent. When you put a stress, these flaws converted into crack. Crack, again if you are putting a stress, crack developed into break. See here, flaws in the particles, unmilled particle. You are not milled so far, just particle as such. Impact. or cutting, whatever it may be, it develops to a crack. See here, it is a crack. How many cracks are there here? Flaws developed to a cracks. Further development, cleavage of the particle to a smaller size, cleavage, smaller particle, and you can see the additional surface. This point is very important. Additional surface you can observe in the break, not in the crack, right? See this wall, how the break up here. This is a break. Here you can see cracks. See how many cracks are there. Before that, here, without microscope, we cannot see. With microscope, you can see. This called as a flash. Flash, cracks, break. Break. It's just like in the movies, they will show no break up. The same fashion. Theories of size reduction. Theory. The energy how much required for a particle size reduction is a function of input. Function means not a Dasara, not a Deepavali here. Function of input and output of the particle size. What is the input of the particle? Either you are keeping this much big particle. What you want? You want very fine particle, a coarse particle. Input, output, hardness of the material, strength, and other properties of a solid. It depends upon various factors. Size reduction, there is a 4 theories are there. These theories, they appeared in number of question paper. They will ask the name, in which chapter it comes, in which concept these theories will come. There are 4 heroes, 1, 2, 3, 4. These 4 heroes, they have developed a size reduction theories. What we will see now. 1, 2, 3, 4. What this fellow say will not agree this fellow. What this fellow will do, developed, this fellow will not agree. And this fellow will not agree to this fellow. One fellow will not agree with another fellow. They will come and they will rightly they will prepare the theories. Keep in your mind. First of all, we will see what are the names of these scientists. Griffith's theory, Bond's theory. Just for your remember, I collected the not, he is not really a James Bond, keep in your mind. So that whenever size reduction chapter will come, in your mind there is a Bond, James Bond, like that. Bond's theory. His name is Rittinger's. His name is Griffith. These two are right. Whereas Bond, and this is also Kick's theory. Kick out. So generally what we will do, if any fellow is doing a mistake and all, we will kick out. Just like a ball. Hitting with the leg is called as a, this one. Kick's theory. 4 theories are there. First theory. Griffith theory. See here, the Griffith. Whenever Griffith comes, keep in your mind, this fellow is very interestingly, one point he told. The point is, first point is, according to Griffith theory, there was a flaw. The word flaw was created by the Griffith. Flaw. This flaw is any structural weakness. What is a flaw in the exam? They will ask for 1 mark question. Flaw is nothing but weakest flaw is any structural weakness that may develop into a crack under the strain. The weakest flaw means weakest part. Here I will show you how to keep in your mind. See his dress design and hairs and all. It looks like a crack. Flaws are there. Flaw. And this point is also very important. According to Griffith theory, amount of the force to be applied depends upon the crack length. Two things are there. One is crack length. How much crack length you want to produce, that much energy is required. If you want a big crack length, you have to produce high energy. And focus on the stress at atomic bond level. See here, stress, atomic bond level. These 2 images you have to keep in your mind whenever there was a Griffith. One is new crack length produced, and another one is a atomic bond stress. And this is the equation. T is equal to, here this is a T, tensile strength is equal to M into PA, Young's module, M into MPa, here you can see. and this epsilon, surface energy of the wall of the crack, epsilon, and C, critical crack path required for fracture. How much fracture you want to produce, like that. Okay. Yeah. Here, the Griffith told two things. What is that? One is crack length. Another one is the stress at atomic bond level. In this concept, bond say only the crack. Only the crack. He will not accept the atomic level bond stress. He didn't accept it. Here you can see, this theory states that energy used in the crack propagation is proportional to the new crack length produced. How much crack length you want to produce? That's why here I put a diagram of crack. How much crack length you want to produce, that much energy is required. Here this is the equation. E is equal to 2 kb minus 1. That's the bond's work index, initial diameter, new diameter. Keep this one. Bond means crack. Griffith means to crack as well as the new surfaces. Stress on the bond. Stress on the bond. And this is a bond's work index that is not required for you, but keeps the second point. This theory is useful for the rough mill sizing, and index is useful for comparing the efficiency of milling operations, but not much important. Rittinger's theory. What this fellow will say, this fellow will not accept the crack length. This fellow will accept the new surface area, how much produced. That's why here I put a diagram. Smaller particle and additional surface area. This is additional surface area. New surface area produced. How much you want to put the additional surface area, that much energy you have to keep. That much energy you have to put inside. This is the equation. So Rittinger's theory means you have to keep in your mind additional surface area. See here, bondless. This surface area you can keep in your mind. He removed here, this surface area came out. Additional surface area. Like that you can remember in your mind. Right? Rittinger's, Ph.D. Additional new surface area. Like that you can keep in your mind. Kick's theory. This is also a very interesting theory. What this fellow say, Kick's theory. Here you take the example of these two. This is the particle I want to put in the ball mill or any mill. And this is desired one. I want this size. In another case, this is the same particle size I will take, but desired size is less. Here, input is the same size, output is a big size here, and output is a small size here. Now, what happened? This much of particle I have to reduce only small, and this much of produce too small I have to produce. So here I need a high energy ratio. Input particle ratio divided by output particle ratio. Here I want to produce the finest particle. That's why I need much energy. So how much energy is required is directly proportional to the ratio by input size and output size. See here, Kick's constant, diameter of the particle of initial stage, diameter of the new particle. This is new particle which is come out. Initial particle. Very simple. And the summary, we can come to that Rittinger's theory. I will show you in the summary. Yeah, this is important slide. And here you can note down in this one, Rittinger's means new surface area. I showed no Rittinger. Bond's theory, crack length. Kick's theory, ratio of the change in the size. These 3 points are very important one. Here you can see this equation appeared in number of question paper in very competitive examinations also. N is equal to 1.0 equation, Kick's theory. The same equation is applicable to all the 3 theories except Griffith. Here keep in your mind, if this N place, this N place, if I keep 1, it becomes a Kick theory. If it is 1.5, Bond's theory. 2 means Rittinger's theory. These constants are very important. Constants appeared in competitive examination, GPAT, drug inspector, all the examination constants came 1, 1.5, 2. And here how to keep in your mind, king, Kick's theory, king. You can keep as a king, K, both K. First one, king is always first. King is always first. So 1, 1. Your constant is 1. B, Bond's theory, keep the B as a code word. B means between. It is a between 1 to 2. So 1.5 between. And 2, Rittinger's theory. See how many T's are there? T, T. 2 T's are there. So 2. There is a clue in the name itself. B means between, K means kings, R means Rittingers. 2 T's are there. Like that you can. In Telugu, it is called as a rendu also. R. R stands for rendu. 2 T's are also there. Okay. Like that you can do. And see what happened when you reduce the size. One interesting point will happen. Solubility increases when you reduce the size. It is a very important in biopharmaceutics also. Big particle size having a lesser surface area, slow solubility, less solubility, slow dissolution. Preferably, we are going, since it is giving a slow dissolution, we are preferable these particles we will try to make a tablets of sustained release particles. Onset of action of a drug is also late because slow release. When you did a size reduction, smaller size you will get, higher surface area, because one particle you reduce it to small, no, surface area increased. Fast solubility, high solubility, fast dissolution, preferable in immediate release dosage form, because particle is size, no, once the tablet is in the mouth, it breaks down, immediately it shows its action. Onset of action is very quick. Just like a Candy Crush or Orange Crush, if you are keeping in the mouth as such, slow dissolution. If you break it with your teeth or crusher teeth, automatically the particles will be come down, break down. So solubility will be immediately will be there. And these are some of the objectives of size reduction. You can take a screenshot. Mainly is to increase the surface area. This point is very important. And also to break the material into small particles and to achieve the intimate mixing also. While doing a size reduction, mixing also happens. And to dispose the solid waste and to remove handle some characters. Okay. And advantages of size reduction, what you will get benefits or advantages. Content uniformity, uniform flow will be there, smooth flow, okay, not zigzag flow, struck flow will not be there. Effective in drying, whenever you are doing a drying, particle size is same, drying will be very easy. Surface area will be increased, okay. Uniform mixing, and some disadvantages also there. Mainly see here, improve the dissolution rate is very important, size reduction. Drug degradation will happen because you are going to be cut the particles, no? So automatically some property will be lost and leads to contamination. There is a chance of mixing of other dust particles inside. And various factors that are going to affect the size reduction. Hardness. This hardness, no? See here, this generally we are using to find the hardness of the Monsanto hardness tester, the Monsanto, Moh scale, MOH, very important and appeared in number of question paper. Which scale is used to measure the hardness? Moh scale. Okay, appeared number of times. See here, for talc powder, just like a pH scale, acid, base. Here also, Moh scale, talc powder having 1, gypsum, and you know that it is having a diamond is a toughest and very hard. So see here 10. As you are increasing the Moh scale number, it is also increasing. Hardness is also increasing. Hardness, Moh scale. In the name itself, there was a clue. MOH. H stands for hardness. And also another factor is there, that is abrasiveness. Abrasive is nothing but rough and tough. Here you can see the powder which is having a roughness. This is also one of the factors that affect the size reduction. Material structure. Some substances are homogeneous in character. See here, all these are homogeneous. Some are fiber-like structure. See here, vegetables, drugs having a cellular structure. You need a cutter mill for this, fibrous type. And softening temperature, at which temperature the material will be softened, that is also going to be important. See here, the material here, it is a solid. When you started heating of it, temperature increases and the material will become a soft and it flow down. See, it flow down. This temperature at which there was a soften is called as a softening temperature. That is also very important. And also moisture content, how much moisture is there in the material to be reduce the size. Okay. And also crushing strength. Crushing strength. Here, how to measure the strength to break down this pellet? It is called a crushing strength. All these factors are going to affect the size reduction process. Friability, stickiness, how much it is a sticky, soapiness, how much it is a soapy, explosives, and also materials yielding the dusts and harmful to the health. We will stop here. Thank you for the breakdown of the particle, crackdown. Crack up leads to breakup. Okay, I will end here. In the next, we will see the size reduction mills.